July 12th, 1944. Outside St. Lo, Normandy. Rain needles the hedgerows as dawn bleeds into a low gray sky. The crack of rifle fire echoes through the bocage, muffled by wet leaves and churned earth. Sergeant William H. Parker of the U.S. 29th Infantry Division presses his helmet lower as his squad advances toward a cluster of camouflaged sheds, half buried under netting and branches. Somewhere inside, a generator hums, steady, mechanical, out of place amid the chaos of retreating German lines. Then the firing stops. A white cloth appears first. Then hands, then faces, young, pale, exhausted. They are not infantry. Their uniforms are cleaner, their fingers ink-stained rather than calloused. One of them stares past Parker at the American Sherman tank idling behind the hedge, its radio antenna whipping in the wind. Radar, the man mutters in German. They have found the radar. The prisoners are technicians. Luftwaffe signals men from a Würzburg-Riese radar station abandoned in haste as Allied forces break through Normandy. Their equipment lies half-dismantled behind them. Parabolic dishes, oscilloscopes, vacuum tubes packed into crates marked with Reich-Sadler stamps. They expected capture eventually. What they did not expect was what awaited them next. By nightfall, they are trucked west under guard, passing convoys of Allied armor, columns moving with an efficiency that feels almost unreal. Overhead, aircraft drone constantly. Fighters, bombers, reconnaissance planes, operating with a confidence that no longer feels reckless. One technician, Obergefreiter Hans Keller, notices something unsettling. The planes fly even in cloud cover, even at night, even when German jammers are known to be active. He says nothing, but he is thinking hard. 3 days later, Keller and several others are escorted into a nondescript Allied operations center. Canvas walls, blackout lamps, cables snaking across the floor. An RAF officer with a clipped accent gestures toward a radar display. It is unlike anything Keller has seen. The screen is sharp, clean. Targets bloom clearly, not as fuzzy smears but as precise points. The range resolution is astonishing. Keller leans forward despite himself. "This is centimeter wavelength," he says quietly, almost to himself. The British officer smiles thinly. Very good. For Keller, the realization hits like a physical blow. German radar, Freya. Würzburg operates on meter-scale wavelengths. Effective, yes, but vulnerable. Vulnerable to jamming, to clutter, to deception. Centimeter-wave radar, by contrast, slices through the sky with surgical precision. Smaller antennas, better resolution, harder to jam. Impossible, Keller thinks. Or it should be, back in Germany, the theory was known. Microwave radar had been discussed in laboratories and dismissed as impractical. Too much power loss, too unstable, too difficult to manufacture under wartime constraints. The magnetrons Germany possessed could not produce sustained, high-power microwave output. The engineering hurdles were considered insurmountable, and yet here it is, working, deployed, everywhere. Another prisoner, Feldwebel Ernst Vogt, asks the question none of them want answered. "How long have you had this?" The RAF officer pauses just long enough to make the silence hurt. "Since 1942, he replies. 2 years. The number settles over the room like falling ash. Keller feels his stomach tighten. 2 years means North Africa. It means the Battle of the Atlantic. It means those U-boats that vanished without warning. Those night bombers intercepted in cloud. Those jamming countermeasures that failed without explanation. 2 years ahead. And this is only the beginning. They are shown more. Airborne radar sets compact enough to fit into the nose of a Mosquito night fighter. Ground-controlled interception systems seamlessly linked to fighter squadrons. Anti-aircraft shells fitted with something Keller has only read about in rumors. Proximity fuses. No need for direct hits. The shell senses the aircraft and detonates at the lethal moment. Vogt whispers, "That's impossible. The electronics, too delicate." An American officer overhears him. "Used to be," he says. Not anymore. What Keller does not yet know, but will soon, is that the heart of all this superiority traces back to a quiet decision made 4 years earlier. Far from the battlefields of Normandy, a decision made in desperation. A small black cylinder of copper and steel, carried across the Atlantic in a locked box, the cavity magnetron. As the captured technicians are led back to their quarters, Keller looks once more at the glowing radar screen behind him. For the first time since the war began, he understands something with terrifying clarity. Germany is not losing because of numbers alone. It is losing because it is fighting the future with the tools of the past. September 3rd, 1940, London, Portland Place. The city still smolders from the night before. Smoke hangs low over the rooftops, and the smell of burned brick and cordite clings to everything. Inside a Georgian townhouse requisitioned by the Air Ministry, Sir Henry Tizard adjusts his spectacles and looks around the table. The men seated with him are exhausted. Physicists, engineers, naval officers. But there is urgency in their eyes that overrides fatigue. Britain is running out of time. Across the Channel, German bombers are probing deeper into British airspace each night. The chain-home radar network has held, for now, but it is bulky, fixed, and vulnerable. The Luftwaffe is learning. Jamming attempts are growing more sophisticated. Britain needs something smaller, stronger, mobile. Tizard clears his throat. "Gentlemen," he says, "what we are about to do may decide whether this war is lost or merely delayed." He gestures to a small metal cylinder resting in a padded case at the center of the table. It doesn't look like much, roughly the size of a grapefruit, machined from copper, riddled with precisely cut cavities. To the untrained eye, it could be scrap. But when powered, it does something no German device can reliably do. It generates high-power microwave radiation. The cavity magnetron is not theoretical. It is real, and it works. Developed at the University of Birmingham by John Randall and Harry Boot, the device produces wavelengths short enough, centimeters, not meters, to revolutionize radar. Suddenly, antennas can be small enough for aircraft, resolution sharp enough to distinguish a submarine periscope from wave clutter, power strong enough to burn through jamming. There is only one problem. Britain cannot manufacture it at scale, not while under siege. Not while factories are bombed nightly and resources rationed to the bone. So Tizard proposes something radical. He will give it away. Within days, a small delegation boards a civilian aircraft bound for North America. In their luggage, carefully concealed, is what one American scientist will later call the most valuable cargo ever brought to the United States. The Tizard mission arrives in Washington quietly. No press. No ceremony, just meetings in secure rooms with men like Vannevar Bush and engineers from Bell Labs, MIT, and General Electric. When the magnetron is powered up for the Americans, the room goes silent. Then someone laughs, not from humor, but disbelief. This, one engineer says, changes everything. By early 1941, the United States throws its industrial weight behind microwave radar. Entire laboratories are reorganized. The MIT Radiation Laboratory is born almost overnight, drawing the best scientific minds in the country. Problems that stumped British engineers, mass production tolerances, cooling, durability under combat conditions, are attacked with assembly lines and funding measured in millions. Germany, meanwhile, watches from a distance, unaware of what has just slipped beyond its reach. Back in occupied Europe, Obergefreiter Hans Keller sits in a makeshift POW camp, replaying these implications in his mind. The British officer's casual mention of 1942 now makes dreadful sense. By the time Germany intensified its electronic countermeasures, Kettenhund, Düppel, noise jammers, the Allies had already moved past the problem. They were no longer fighting radar battles in meters. They were fighting in centimeters. Keller remembers reports from U-boat commanders, sudden aircraft appearances, attacks delivered with uncanny precision, even in fog or total darkness. At the time, High Command blamed espionage, luck, or exaggerated enemy claims, radar detection. Yes, but nothing revolutionary. Now Keller knows better. The Allies were not reacting. They were dictating. The realization deepens weeks later, when the technicians are shown fragments recovered from German aircraft shot down over England. Embedded in the wreckage are tiny, shattered devices, proximity fuses, American-made, each one a marvel of miniaturization. Vacuum tubes rugged enough to survive artillery firing, circuits calibrated to sense reflected radio waves from an aircraft's fuselage. Germany tried to develop similar technology. It failed. Too complex, too fragile, too many components, each one a potential failure point under combat stress. German industry, strained by resource shortages and bureaucratic infighting, simply could not match the Allied pace. And pace is everything. By 1944, Allied microwave radar is everywhere. In bombers navigating through cloud to strike industrial targets, in night fighters stalking Luftwaffe aircraft with invisible eyes, on ships scanning for periscopes that barely break the surface. Electronic warfare is no longer a duel of clever tricks. It is an ecosystem, and Germany is outmatched at every level. One evening, Keller overhears an American guard chatting casually. "My brother's in the Navy," the man says. "They say the new radar can pick up a snorkel from miles away." Miles. Keller closes his eyes. 2 years. He thinks again. 2 years behind. And the gap is only widening. March 6th, 1943. 23,000 feet above the North Sea. The B-17 Hell's Kitchen shudders as flak blossoms below, black puffs clawing at the sky. Inside the bomber's nose, Lieutenant Charles Red Lawson peers through the plexiglass, gloved hands steady on the Norden bomb site. Outside, clouds swallow the formation in rolling gray waves. Visibility drops to nothing. In 1941, this would have meant aborting the mission. Not today. A soft, rhythmic pulse fills Lawson's headset. Steady, reassuring. On the radar scope mounted beside him, coastlines appear as ghostly outlines. Rivers snake inland. A city resolves from the noise, its shape unmistakable. Bremen, Lawson exhales slowly. "We're on track," he says into the intercom. "Hold course." The radar feeding that image is H-2S, an airborne, ground-mapping radar operating at microwave frequencies, powered by the cavity magnetron. Below the cloud layer, German defenses wait blindly. Searchlights sweep empty sky. Flak batteries fire based on sound and guesswork. Shells bursting too early or too late. The bombs fall anyway, far below. Oberleutnant Karl-Heinz Richter of the Luftwaffe listens to reports crackle across his radio. Radar stations are confused. Jamming is heavy, but the usual countermeasures aren't working. Würzburg sets show interference patterns they cannot interpret. Targets appear, vanish, then reappear somewhere else entirely. "Are you certain of the range?" Richter demands. The answer is hesitant, uncertain. That hesitation is fatal. Across the Atlantic, the turning point has already been recognized. In Washington, analysts note the shift in loss ratios. Allied bombers are finding targets more reliably. U-boat sinkings spike sharply. Night fighters are claiming kills at rates previously thought impossible. The cause is not a single weapon, but a convergence. Microwave radar shrinks the battlefield. In the Atlantic, German submarines surface at night to recharge batteries, trusting darkness and cloud cover. But Allied aircraft now carry ASV Mark III radar, its antenna small enough to fit under a wing. A faint blip appears on the screen. A conning tower, barely breaking the waves. The attack comes without warning. One U-boat commander survives long enough to send a final transmission. "Enemy sees us at night. We are no longer safe on the surface." He is right. Germany responds as best it can. Radar decoys are deployed. Jammers are upgraded. Strips of aluminum foil, duple, known to the British as window, are dropped to confuse radar screens. For a brief moment, it works. Then the Allies adjust. Centimeter wave radar is harder to fool. Filters are refined. Operators are trained to read through clutter, New frequencies are introduced before German intelligence can respond. Each countermeasure triggers a faster, more effective countermeasure. It is not just technology, it is process. The MIT Radiation Laboratory alone employs thousands of scientists and engineers, all focused on solving problems in weeks that once took years. Prototypes go from lab bench to combat aircraft in months. Feedback from crews is folded directly into redesigns. Germany's system cannot keep up. By late 1943, the imbalance is stark. Allied anti-aircraft guns fitted with proximity fuses detonate shells at precisely lethal distances. German aircraft fly through flak that no longer needs to hit them directly. The sky itself becomes hostile. Captured Luftwaffe pilots speak of radio mines in the air. They are not far off. In the POW camp, Hans Keller finally receives confirmation of what he suspected. An Allied intelligence officer, perhaps feeling magnanimous or simply confident, lays it out plainly. "You focused on perfecting what you already had." The officer says, "We focused on what came next." Keller thinks of German laboratories arguing over theoretical purity, while American factories churned out magnetrons by the tens of thousands. He thinks of reports dismissed, warnings ignored, funding delayed. He thinks of how close Germany had come and how decisively it had fallen behind. The turning point was not a single battle. It was a moment when one side embraced uncertainty and acceleration, while the other clung to proven designs. From that moment on, the outcome of the electronic war was decided, and without electronic superiority, the rest of the war followed inexorably. October 18th, 1944, RAF Station Bautzen, Suffolk. The wind off the North Sea carries the smell of salt and cold metal. Inside a reinforced operations building, a group of men in mismatched uniforms stands quietly around a long table. Some wear Luftwaffe insignia stripped of rank. Others are Kriegsmarine specialists. All of them are prisoners. At the head of the table, an American civilian adjusts his tie. Dr. Luis Alvarez, physicist, radar engineer, future Nobel laureate, taps a folder thick with schematics. "Gentlemen," he says evenly, "we're going to show you something." The lights dim. On the wall, a projection flickers to life. It shows a gun barrel in cross-section. Inside it, an artillery shell spins violently as it is fired. Within the shell, impossibly, are tiny vacuum tubes, coils, and a power source. The image pauses at the moment of detonation. This fuse, Alvarez continues, does not wait to hit its target. It listens. A murmur ripples through the room. The German technicians lean forward. They know what they are seeing. They also know what it means. The proximity fuse emits a radio signal. When that signal reflects off an aircraft and returns at a specific strength, the circuit closes. The shell explodes at exactly the right distance to shred aluminum and flesh alike. No direct hit required. For Germany, this had been a theoretical concept, a laboratory curiosity. Too many variables, too much vibration, too much heat. No way to prevent premature detonation. Alvarez clicks to the next slide. By the summer of 1944, he says, we were producing over 20,000 of these per day. The number lands like a blow. Hans Keller watches Vogt's hands clench into fists. 20,000 a day means more than engineering success. It means logistics, quality control, redundancy. It means failure rates low enough to trust the weapon in combat. It means an industrial ecosystem aligned with scientific ambition. Outside, the sound of aircraft engines rolls across the airfield. A Mosquito night fighter lifts into the dusk, its radar operator already scanning the sky. In its nose, a compact microwave radar set hums quietly, its magnetron glowing unseen. Keller thinks back to his student days, to German professors dismissing American engineering as crude but plentiful. They make tractors, one had scoffed, not precision instruments. The memory tastes bitter now. After the presentation, the prisoners are escorted to a radar hut. Inside, a live demonstration is underway. An operator adjusts a dial. A blip appears, small, sharp, unmistakable. Fishing trawler. the operator says casually. 8 miles. 8 miles. Through mist. With an antenna no larger than a dinner plate. Keller cannot stop himself. When did you solve the stability problem? He asks. The operator shrugs. Early 42, maybe late 41, depending how you count. 2 years. Again, that night, Keller lies awake, listening to the distant surf and the occasional thud of bombs falling somewhere across the channel. The war is still raging, but in his mind, it is already over. Not because of Normandy, not because of the Red Army, because Germany lost the invisible war. Radar, fuzes, navigation, jamming, counter-jamming. These are not dramatic on their own. They do not inspire parades, but they shape every engagement before the first shot is fired. By the time German commanders realize their aircraft are being seen before takeoff, their submarines hunted before surfacing, their defenses bypassed rather than smashed, it is too late. The reckoning is not a single revelation. It is a slow, grinding awareness that the enemy has been living in the future while you fought in the present. Keller understands now why Allied officers are so calm, why they explain things so openly. Secrecy no longer matters. The gap is unbridgeable. May 9th, 1945. Göttingen, Germany. The war is over. In a university lecture hall spared by bombing, folding chairs scrape against stone floors as a small audience gathers. Allied officers, civilian scientists, former Wehrmacht engineers now stripped of authority and certainty. Outside, the town is quiet in a way that feels unnatural, as if sound itself has been rationed. At the front of the room stands a blackboard. Chalk dust floats in sunbeams cutting through shattered windows. Hans Keller sits in the third row. He is no longer a prisoner. He is no longer an enemy combatant. He is something else now, an artifact of a defeated system, summoned to explain what went wrong. An American major nods to him. You worked radar countermeasures, he says. Explain to us why Germany failed to keep pace. Keller stands slowly. He feels older than his years. He begins not with equations, but with culture. We believed, he says carefully, that superiority came from refinement, from perfecting what already existed. Our radar sets were precise, elegant, but they were also fragile, in more ways than one. He draws 2 lines on the board, one long and continuous, one jagged, branching wildly. The Allies chose the second path, he continues. They accepted instability in order to gain speed. They allowed failures, wasted effort, duplication. We did not. Around the room, heads nod. Post-war analysis will confirm what Keller is saying. German science was world-class, but compartmentalized. Rival agencies competed instead of cooperating. Promising projects died in committees. Industrial scale lagged behind innovation. The Tizard Mission becomes a case study taught in military academies for decades to come. A moment when secrecy was sacrificed for survival. And the gamble paid off beyond measure. British cavity magnetron technology did more than win battles. It reshaped warfare itself. Navigation by radio, precision bombing, air traffic control, weather radar. Even peacetime aviation owes its safety to decisions made under blackout curtains in 1940. As the lecture ends, Keller steps outside into the cool spring air. Bells ring in the distance. Church bells, not air raid sirens. He looks up instinctively, half expecting bombers. There are none. Years later, an American report will summarize the matter with brutal simplicity. Allied victory in electronic warfare shortened the war by years and saved countless lives. But Keller knows the truth is more human than that. It is about listening when a young engineer says, "This might work," about funding an idea that seems impractical, about recognizing that tomorrow's war will not be fought with yesterday's tools. The German scientists who first encountered Allied microwave radar in 1944 were not shocked because it was better. They were shocked because it already existed, because while they debated whether it was possible, the Allies had already built it, deployed it, refined it, and moved on. In war, as in science, being 2 years behind can mean being forever too late.